This is Moser with a tutorial called Matter. Mix it up. By the end of this tutorial, you should be able to explain the difference between a pure substance and a mixture, describe how mixtures can be separated based on their physical properties, and it's probably a good idea to know what the kinds of mixtures are too. You should already know what matter is and the difference between chemical and physical properties. Since we're assuming that you do know what matter is, you know that all of these things are composed of matter. We have baking soda, the box, the cardboard box, is matter, as is the baking soda itself. This lovely little stainless steel coffee pot, made of matter, including its plastic handles. Vinegar, the glass bottle, the plastic cap, and the vinegar inside are all made of matter, as is the paper label. This weird blue Kool-Aid is matter, as is the glass pitcher it's in, the tablecloth it's sitting on, and the ice floating in it. This rock is matter, you knew that. The pasta salad, the bowl, the spoons, all matter, and so is this comfy chair. Now, if only there was some way to classify them a little bit further than that. Well, there is. Hey, look at that. When you look at any piece of matter, the first question to ask is, can it be physically separated? If the answer is no, then you're dealing with what's called a pure substance. A pure substance is all one thing. So, can we go further than that? Yeah. When we look at a pure substance, we want to ask, could we break this apart using ordinary chemical means? Could we undertake a chemical reaction and break it apart? And if the answer is no, then we're looking at an element. So the elements are the things on the periodic table. We'll talk more about them later, such as gold, aluminum, oxygen, nitrogen, chlorine, pure carbon. And these are all things that can exist in a quantity of a single atom. If the answer to the question, can it be broken apart by ordinary chemical means, is yes, then we're talking about a compound. And a compound is one or two or more elements that have been joined together chemically. The sodium bicarbonate inside this box of baking soda is a compound. This is acetic acid and water. The acetic acid is a compound, as is the water. The ice cubes floating in this pitcher are water, a chemical combination of hydrogen and oxygen. When we talk about a pure substance, whether it's sodium bicarbonate, baking soda, or water, or anything else, or an element, we know that they have a fixed composition. That means what they're made up of doesn't change. And they're different from a mixture in that any time we take a sample of a pure substance, it's going to have the same exact properties. Every sample of a pure substance has the same composition. This is table salt, sodium chloride. It's a pretty familiar compound to most of us. And no matter where on the planet the salt came from, it's going to have the same chemical properties, it's going to have the same solubility, it's going to have the same conductivity, and it's going to have the same melting point. That's a pure substance. They are so predictable. Well, now, let's go back to our classification, and let's talk a little bit about if our answer is yes. So when we look at matter and we ask if it can be physically separated, if the answer is yes, then we're dealing with a mixture. And a mixture has more than one pure substance that's just been physically combined. When we have mixtures, we want to ask ourselves if the composition is uniform. If the answer is no, then we're talking about a heterogeneous mixture. The prefix hetero refers to different, and a heterogeneous mixture has a different composition throughout. This rock is probably a heterogeneous mixture. Very often within a rock we'll find crystals or other minerals that have accumulated, and they're not all evenly distributed. That means that the composition of the material is not the same throughout. What other mixture in this little assemblage here do you think would be heterogeneous? I'll give you my guess. This pasta salad looks delicious. And I can tell you that no matter how hard I try, if I take a spoon of it, I'm going to end up with a big plate full of whatever ingredient I like least. So we have pasta and olives and little tomatoes and parsley and cheese and salami. I really hate salami. But I bet I'll get a disproportionate share of it. So it's a heterogeneous mixture. The composition is not the same throughout. So if we take a sample of it, it's entirely possible that we won't get an even distribution. That's the problem with heterogeneous mixtures. If we look at our mixture and ask about the composition being uniform and the answer is yes, then we are talking about a homogeneous mixture. Prefix homo means same, and a homogeneous mixture has the same composition throughout. Air is a homogeneous mixture. Lucky for us. If not, you might stumble into a big nitrogen pocket and die. Stainless steel is an interesting homogeneous mixture. It's what we call an alloy. And an alloy is simply a heterogeneous mixture of two or more metals. We use a lot of them. On this page, the Kool-Aid in this pitcher we would assume is a heterogeneous mixture. When you take a glass full of Kool-Aid, every glass should taste the same because the sugar, Kool-Aid powder, and water should be evenly distributed. That's a special case of a heterogeneous mixture that we call a solution. There's one other solution on this page. Can you guess what it is? It's the vinegar. As I said, vinegar is a mixture of acetic acid and water. Both compounds, by the way, but they're mixed to form the solution that we know as vinegar. Okay, so let's talk a little bit about those mixtures and how we can separate them. When we have a mixture and we want to separate the various component pieces, we have to look for differences in the characteristics of the materials. Some mixtures can be separated by hand. This raisin bread could be vastly improved, in my opinion, by picking out every single one of the disgusting raisins. Not that I have strong feelings. It's a mixture of bread dough and raisins and cinnamon and other things, but we could pick the raisins out because they're easy to see, they're physically of a size that would allow us to do that, and there's no reason not to. Very few of the mixtures that we would encounter in a chemistry lab can be separated by hand. Take this, for instance, a combination of tiny pink beads and iron filings. Ugh. The particles are all very tiny. It'd be nearly impossible to separate by hand, but we could separate them because they have a different characteristic in regard to magnetic attractiveness. The iron filings are attracted to a magnet, while the pink beads are not. Again, it's based on a difference. Now, what if you have this pasta and water, and you want to separate the pasta from the water at the end? Well, I think most of us would just put it through a filter, such as this strainer. We often filter mixtures in the lab, though we're not typically filtering based on the size of the particles difference, which is how we're separating the pasta. We're usually filtering based on differences in solubility, whether one thing will dissolve in a solvent and the other won't. When we have two materials in a mixture that have different solubilities, we can add the solvent to that mixture, allow one of them to dissolve, and then pour the whole thing through a funnel with filter paper. The thing that is non-soluble will stay in the filter paper, while the thing that is soluble will travel through with the filtrate to the beaker. You may have done this recently. The final method for physically separating a mixture is heating based on differences in their heat of vaporization. If two substances boil, go from a liquid to a vapor at different temperatures, or sublime, go from a solid to a gas at different temperatures, then we can take advantage of that to heat them above the point at which one will vaporize. What does that look like? When we have a number of substances in water, any sort of things like acetic acid, such as vinegar, or alcohol, or salt or sugar, we can separate the water from the other substances by taking advantage of differences in their heat of vaporization. So if we apply heat to this mixture, the lighter particles will start to vaporize first, leaving only the heavier particles. In some cases, we want to actually capture the lighter particles as well, which we can do, and then we can recondense them. But very often, we're just looking to separate out the particles of whatever that other material is. Okay, that's separating a mixture based on physical characteristics. You're ready to actually separate a mixture based on physical characteristics.